The last couple of videos, we've talked about some cubic equations of state. So I've summarized them for you neatly here. We talked about van der Waals in the first video. We've talked about Pang-Robinson, and we solved for volume in the Pang-Robinson using Excel on the last video. Also wanted to give you the Suave-Redlich-Kwong equation of state. This is just a small sampling of the many different equations of state that exist. I want to point out the similarities between these three. So these three are in the same family of equations of state, which are termed cubic equations of state, because the volume term, if you solve for it, would be third order. I wanted to highlight the similarities in that they have the same repulsion term. So in all three of these equations of state, you've got RT over V minus B. And you have slight differences in the attraction term. So van der Waals, Pang-Robinson, and Suave-Redlich-Kwong all use slightly different variants of that second term. Pang-Robinson and SRK were derived, or they were empirically formulated after van der Waals. They've kept the same meanings for the constants just to have similarity between them. So remember that the A constant denotes attraction. So A is oftentimes termed the attractive constant, and B is the repulsive constant. So remember, another way to think about B is that it represents the minimum volume that the molecules must occupy. In other words, if V under bar is less than B, then you've got a negative term, and subtracting a negative term makes the pressure a negative, which cannot be physically true. So V under bar has to be greater than B. Importantly, we haven't talked about temperature dependence yet, but in Pang-Robinson and SRK, the A parameter is a function of T. So A is equal to F of T. We breezed over that in the Excel problem that we just did, but in general, you should take note that A is a function of temperature. This is important because if we look at these pressure versus molar volume plots, we see for temperatures that are less than the critical temperature, we see behavior similar to what we saw in Excel. In other words, we go all the way down, we have a minimum, and then we have a maximum, and then we start leveling back off again. So again, these are for these curves that go down and have a minimum and a maximum are all for temperatures that are less than the critical temperature. So this is a phase diagram of P versus T. The critical temperature is there, so it goes all the way up. And below the critical temperature, so on the left side of this graph, all this part, a fluid can exist as a liquid or a vapor. So that's why there is differences between them. So in other words, for this bottom curve, for example, we might say that this is the the vapor pressure corresponding to that temperature. These curves are all isotherms, meaning for constant temperature. So in this curve, temperature is being held constant, volume and pressure are changing. The saturation pressure increases as temperature increases. So these curves going this way are for increasing temperature. So for each one of these curves, we might find that the saturation pressure is just a little bit higher than the last one. All the way up till the point that we hit the critical temperature. So that is what this says. T is equal to TR, which is corresponding to the critical temperature. Above the critical temperature, we don't say that a fluid is a vapor or a liquid anymore. It's a supercritical fluid. So for a supercritical fluid, we have a very smooth curve that doesn't have a minimum or a maximum. And so why this is, I'll talk about in a second. But first, I wanted to show you this in the equation of state solver that we already did in Excel. So I'm going to zoom out a little bit, and I'm going to turn my maximum pressure up to 100 so that we get a better idea for the graph. And then I'm just going to change temperature. So I'm going to increase temperature and see what happens to the curve. So maybe we try 500 Kelvin, and we see that the curve is increasing. All right, maybe let's try 800, still the same thing. 1,000, oops, I meant to say 1,000. And as I keep going up and up to the critical temperature, at a certain point, I'm going to have a smooth curve. So I have to zoom out even further in order to see this. So maybe I'll go up to 500. Right, and you may be able to discern that there's still a little bit of a jump, but as I increase further and further and further, it gets smoother and smoother and smoother as I go up towards that critical temperature. So as for why we see this difference in behavior as temperature increases, remember that for any curve, once you hit the saturation pressure, so let's say that that occurs here for the lowest temperature, all this part of the graph that I'm highlighting is not actually physically relevant. It's just there such that the curve can be continuous. In a real process, the data that we would see would be the red part. So it would trace this part of the curve, and then when it hits this saturation pressure, it would immediately jump over to this side. So remember, this is the vapor side, this is the liquid side. But as we get up to that critical temperature, so if the temperature is up here and we start increasing the pressure, there is no more phase transition. In other words, the actual data would follow this exact curve for temperature is greater than the critical temperature. I did not do a very good job tracing that line at all. So something like this. For a temperature where the temperature is greater than the critical temperature, there is no jump that's occurring from vapor to liquid. So there is no local minimum or local maximum. So the local maximum would be, this is what I'm talking about. That would be the local maximum. This would be the local minimum. Neither of these are physically relevant, again, for a fluid. It's just arising due to the nature of the cubic equation of state. And we want to be able to model the vapor and the liquid with the same equation of state. So that's why we use a cubic equation of state. So next, I want to talk about how to find values of the parameters A and B if the problem doesn't come right out and tell you what they are. And I want to illustrate that process for water. All right, so the critical temperature and pressure for water is given, that's looked up, and we want to determine the van der Waals parameters of A and B, and also we want to find the compressibility at the critical point as well. So compressibility at the critical point is Z sub C. So back up to this chart, notice that as we increase the temperature, that the maximum and the minimum are getting closer and closer as the temperature continues to increase. So the maximum is going further left, the minimum is going further right. And at T is equal to TR, they come together at a saddle point. So at the saddle point, we have from calculus, it tells us that the second derivative, so d2p over dv2 is equal to 0 for the saddle point. We're going to use that fact in order to do our solutions. Okay. All right, let's start with the van der Waals equation. Van der Waals equation of state is P equals RT over V minus B minus A divided by V squared. All right, let's take the derivative of that with respect to V. We will have to take the derivative in order to get the second derivative. So dP dV is then, so we've got a V minus B in the denominator. So we can just as easily say that this is in parentheses and to the -1 power in the top. So that -1 is going to come out front. So it's RT over V minus B squared. And then we would have to do the inside derivative, but the inside derivative with respect to V is 1 because there's no coefficient on the V. And the derivative of the second term is V to the -2, so that -2 comes out front. Negative, the negative makes it a positive, plus 2A over V cubed. So that's the derivative. The second derivative, d2p over dv2, is equal to, now the -2 comes back out front again, making it a positive. So it's 2RT over V minus B to the third power plus -6A over V to the 4. Forgot my underbars. All right, so because we're at the critical point, so we're going to assume that at T is equal to T critical, we said that this is at a saddle point, so therefore this second derivative is equal to 0. And also the first derivative is equal to 0 as well, because the slope is flat at that point. All right, so note that these are both for the critical point. So in order to make this equation proper, we should have to plug in the critical temperature and the critical pressure and the critical volume. So all these variables of state should be C's. Temperature critical, volume critical, volume critical, volume critical, temperature critical, volume critical. And this subscript just means the molar volume at the critical point, the temperature at the critical point, etc. We know what TC is from the problem statement. You could also look that up. So how many degrees of freedom do we have in these set of equations? So just from these two equations, I count 3 unknowns. And my 3 unknowns are the parameters A and B that we were trying to find, and we also don't know the critical molar volume. So unfortunately, because we only have 2 equations, that means we are going to need another equation. But I forgot about one equation. So minus, it looks like 2 equations, but I just gave away that there's another equation. What is another equation that we could use to solve for the molar volume? It's the equation of state itself. So I can apply this equation of state to the critical point, and I could say that PC is equal to RTC over VC minus B minus A over VC squared. So instead of 2 equations, we have 3 equations, and we are solving for all these. All right, solving this system of 3 equations for 3 unknowns, A, B, and the critical molar volume. So it looks to, this is a little bit involved of a process. I'm not sure I want to show you all the algebraic steps in the interest of making the video shorter, but I do encourage you to go through and see that you can solve these, and I'll just give you the simplified forms. So if you go ahead and solve for A in terms of the things that we know, so I'm not going to plug in these numbers quite yet, right? You can show that for the van der Waals equation of state, A is equal to 27 over 8 times RTC times B. And you could also solve for, oh wait, this is in terms of B. This is not what I want. I accidentally gave you an intermediate value. One moment. All right, so we want the parameters of A and B in terms of all things that we know. So I don't want A in terms of B. Instead, I want to say that A is 27 over 64 times R squared TC squared over PC. And this is in terms of all stuff that we know. So we know the gas constant, critical temperature, critical pressure are given to us. B, the parameter, is equal to RTC over 8PC. So in that expression that I gave you before, you should be able to just plug in this B to this B, and then you could get back that expression for A that's here. And then critical volume in terms of the critical temperature and critical pressure. So V bar C is equal to 3/8 RTC over PC. So we can plug in the values of critical temperature and critical pressure and say that for water, the values of the van der Waals constants are A is equal to 5.52 times 10 to the 6th bar centimeters to the 6th per mole squared. And B is equal to 30.4 centimeters cubed per mole, just by plugging in the values of T and C, TC and PC. Now the compressibility, ZC, for water, is equal to PCVC over RTC. And now we have all those terms. So we can do some mathematical fiddling to get rid of the VC, and we could get PC over RTC, and then just simply plug in the value of VC that we got from above. So that's 3/8 RTC over PC. And for water in this case, we get a compressibility of 0.375. So this illustrates how the values of A and B, by the way, these values of A, B, and VC, these are not just good for water. These are good for any compounds that obey the van der Waals equations of state. So for each equation of state, you can go through a similar process and you can derive values of A and B. But importantly, remember that only for van der Waals is A constant. So for van der Waals, A is not a function of temperature, but for Pang-Robinson and SRK, the value of A should be a function of temperature. And that helps with the temperature dependence. So one of the reasons why the van der Waals equations of state isn't as accurate as the other two is that it fails to take into account all this temperature dependence. In other words, because the parameters of A and B are oftentimes fit for the critical temperature and critical pressure, the van der Waals equations of state will be most accurate near the critical temperature and pressure. As you get further and further from the critical temperature, the fit starts to break down a little bit, and that's why it's not quite as accurate. And that's why modern equations of state, like Pang-Robinson and SRK, are generally seen as more accurate and better used. One more equation of state that I want to talk about that is not cubic is the virial equation of state. The virial equation of state, notably, is only good for vapors. So you have the same problem that you had with the virial equation of state that you had for the ideal gas law equation of state, that you can't use it for liquid. So the cubic equations of state are good because they're for both vapor and liquid, but virial is not so. Virial equation of state is usually written in terms of Z, and it's Z is equal to 1 plus B over V underbar plus C over V underbar squared plus D over V underbar cubed, so on and so forth. So you can go as far out as you want, and each one of these terms is adding a little bit of accuracy, but each one of these terms is less and less important. This is analogous to a Taylor series expansion, and you call B, C, and D the virial coefficients. So I wanted to note that the virial equation of state is oftentimes better than the ideal gas law equation of state. You may also see it in unisim a lot, but be aware that the virial equation of state is only good for gases, or vapors more properly. And another reason why I note it is because that all the other equations of state that we've talked about, Suave-Redlich, Kwong, Pang-Robinson, those are empirical. I'm going to quickly talk about the difference between empirical and theoretical. So an empirical equation is derived based on observation or experiment based. Whereas the virial equation of state is more theoretical, as the name implies, based more on theory. Now that said, the virial equation of state is not actually used in practice most often because the empirical equations of state happen to fit real data more, so that's why we use them more. All right, this video is getting a little bit long, so I'm going to cut it off there, and I'll see you next time.